Now when it comes to functions, we generally save three special letters to denote the functional relationships. We may have y is f brackets x, and that's the one we tend to use. But there are other letters, and I want to show you how we might use those. The y might also equal g of x, or y might equal phi of x. Those are the three that we tend to use. And all of these just represent a different functional relation. Very rarely do we ever need more than three. Now imagine that we were doing an experiment. And the experiment was looking at how the kinetic energy of a moving object depended on some quantity, the nature of which we were uncertain of. What we could say is that the kinetic energy was equal to the function of this quantity x. We don't know what x is at this stage, but looking at how x changes the potential energy, we would put different values of this as an independent variable, and this would be dependent on it. And the link between the two would be this function. We could test that link. We might find that f was equal to a half m, meaning that this relationship was actually that the potential energy was equal to a half mx. But then we would see that x by itself is not an individual quantity, that x is in fact a function of something else. And so therefore we would have to use one of these symbols to represent a different function being present in our relationship. What we would say is that x in this relationship was actually equal to a function that was dependent itself on the quantity v. And in fact, it doesn't take a genius to work out that this, in fact, is equal to v squared. And so it seems that this function has a function within it. It is a function of a function. And how would we write that all out in this notation? We would say that the kinetic energy was equal to F, and now we can't have too many brackets here, so we can use braces instead. F of phi, brackets, V, close brace. Or, as you and I are more familiar with it, the kinetic energy is equal to F, which is a half m, function of phi, which is v squared. The kinetic energy is a half mv squared. So our function y equals f of x. Imagine this is an experiment that we might be doing in science. We could perhaps draw a graph like this, with y being the dependent variable, x being the independent variable, and we could find that the graph looks something like this. And what we would find out is that there is a functional relation between the two quantities. Now, in mathematics, we might call these two axes on this graph slightly different names. We would call the x-axis the domain, and we would call the y-axis the range. For the sake of the physical sciences, independent variable and dependent variable are more related to an actual experiment that we might do, so we will use that terminology onwards. But for any particular value of the independent variable, we can, through this function, work out a value of the dependent variable. In this particular example, y is equal to 2x, and so there we have it implicitly defined and explicitly defined. Y is explicitly defined in terms of x. But I wonder whether or not we could define x explicitly from y. Now, in the physical sciences, we know this simply as rearranging the formula to make, in this case, the independent variable subject to the equation. Now, in this particular example, all we would need to do is divide both sides by 2. So we would find that y divided by 2 is equal to x. We would find that this expression, in terms of x, is the inverse function of the original function that we drew this graph from. The notation for this would be that x is equal to the inverse function of y. Now for this single uniform function, it's really quite obvious that one value of x is going to produce one value of y, but it doesn't have to be so. We can use a multiform. How about a multiform function that has two solutions for x for a given value of y? Well, take for example the straightforward graph of y equals x squared. And now what you can see is for this particular function, if we were to rearrange this, we would simply have to undo the square, so we would square root both sides. We would square root y and we would square root x squared. The square root of x squared would equal x. And so therefore we would have square root of y equal to x. And this is obviously in third form, and we want to put it in a different notation. So recognizing that square rooting something is raising something to the power of a half. Now that is part of this, but it's not the entire solution. If you think about it, raised to the power of a half, the inverse of this is going to have two possible solutions, and they are going to be plus y to the half and minus y to the half, representing the two solutions of this multiform function. So plus and minus y to the half, in this case, will equal x. And what you can see is that there should never be a value of x that produces a negative answer for y. And so a negative answer for y cannot go into this equation and produce a positive value of x. The only way that we could do it is if we decided that none of these were real numbers and that there was an imaginary plane. So here we have it. The inverse function is simply the function that undoes the work of the function. It's the function that enables you to get to the independent variable from the dependent variable, or to get to the domain from the range. So what about those trigonometric functions that are so multiform that they have an infinite number of forms? For example, y equals sine x. For example, now you're familiar with y equals sine x, that y is here, x is here, and you have this pattern that repeats itself again and again and again and again, and like this, with pi radians being here, 2 pi radians being there, and pi over 2 radians at the top there. Now you can see that any particular value of x will only produce one value of y. But what you can see is that the inverse function of this is going to cause problems, because any one value of y will produce multiple values of x. So how does this work? Well, when we do the inverse function of this, the x being equal to sine to the negative 1 of y, the inverse function of y, then the y that this will produce, or if you feed in this y, the x that this will produce, normally if you did it on a calculator, would be the first one that occurs in the series, normally the one between pi over 2 and minus pi over 2. So x would fall very much in the range of minus pi over 2 and positive pi over 2, the first occurrence of that. And this is called the principal value of this inverse function. Now that is the very first value, but there are more values that are actual solutions to this. There is the next one, and then the next one, and then the next one. So if we were to write this out more formally, we would have to write out that x was equal to inverse sine of y, but then we would want the next occurrence where this was true, and that would happen a whole cycle later. And we'd multiply it by n, integer value, because it would then happen again another 2 pi later and another 2 pi later. And of course it would happen this way as well. The formula is more complex, but not really. 2n minus 1 times pi minus inverse sine of y. This would give you all of those occurrences where this was true in the negative part of this graph.